For 100 years, atoms were the surest thing in science that no one had ever seen. Real beyond doubt, and on any ordinary surface, utterly invisible. Then, in a Zurich lab, two physicists held a metal needle a breath above a surface, never touching it, and read a faint electric whisper leaking across the gap. That whisper drew a map, individual atoms in plain view, and soon the same needle would nudge them about, one at a time, like beads. By 1980, no one doubted atoms were real. But real and seen are different things. Everything we knew of them came sideways, from how they scatter X-rays, from the light they give off, from the equations. Always an average over billions. Never one atom, fixed to one spot on a real surface. And the reason is simple. To resolve a thing, your wave must be finer than it is. Visible light ripples in waves thousands of atoms wide, far too coarse. So the field was starving for a way to stop inferring and start seeing. So here is the question they set themselves. Not the average, not the diffraction pattern. Could you map real atoms, one at a time, exactly where they sit? A picture you could point at? Their answer began with a quantum trick. Bring a sharp metal tip within a nanometre of a conducting surface. Close, but never touching. In our world, no current can cross that empty gap. In the quantum world, it can. An electron can simply appear on the far side of a wall it hasn't the energy to climb. Physicists call it tunneling. Across the vacuum, a tiny current flows. But this current answers to just one thing: the width of the gap. Draw the tip closer by a single angstrom, a 10/1000th of a meter, less than the width of an atom, and it leaps roughly tenfold. So think what that means for the very end of the needle. Whichever atom pokes out closest carries almost the entire current. You are not reading with the needle. You are reading with its one frontmost atom. One atom, feeling for another. Now, you have to move this atom-sized feeler without a single stumble. The tip rides on crystals that stretch when you apply a voltage by fractions of an atom, smooth as breath. It rasters back and forth. A feedback loop watches the current every instant and lifts or drops the tip to hold it dead constant. Trace those tiny height corrections across the surface, and you have drawn the landscape, atom by atom. One catch: a passing truck, a footstep, a voice would drown it. So the first machine floated free, hung on a magnet in near silence. Then, in 1982, silicon. They aimed the tip at a clean silicon surface and scanned. And out of the noise rose row upon row of individual atoms locked in a pattern of sevens, the famous 7x7. A reconstruction people had argued over for years, read only from blurry diffraction. Here it was, in the open. The first time anyone had looked at a surface and seen its atoms, one by one. The nanoscale was open, to sight and then to the hand. The idea threw off a whole family of probes. Its closest cousin, the atomic force microscope, gave up the current entirely. It feels the faint forces between atoms instead. And so it reads what the tunneling tip never could: insulators, plastics, even living cells. Then, in 1989, the astonishment. Researchers slid 35 xenon atoms into place, one by one, and spelled 3 letters: IBM. Later, they fenced electrons inside rings of atoms and watched them ripple into standing waves. In 1986, Binnig and Rohrer took the Nobel Prize, sharing it with Ernst Ruska, father of the electron microscope. What makes it beautiful is where the power came from. Tunneling was a ghost from the 1920s, a paradox on a chalkboard, electrons passing through walls, of no use to anyone. Binnig and Rohrer took that paradox and made it a ruler. They didn't build a better lens. They gave up on light entirely and chose to feel the surface instead, with a current and a single atom. To see the smallest things, they stopped trying to look and reached out to touch. Beautiful experiments.